Telemetry from America's first satellite had just delivered a result that should have been impossible. A radiation detector orbiting above Earth was recording strong bursts of activity. Then, without warning, the signal collapsed into a perfect flat line. Absolute zero. No radiation. No noise. Nothing. Inside the control rooms of NASA engineers stared at paper printouts feeding steadily through their consoles, trying to understand a terrifying possibility. America's first major victory in space may have already failed. It was early 1958, and the pressure surrounding Explorer 1 was unlike anything the American scientific community had ever faced. Just months earlier, the Soviet Union had launched Sputnik crisis into orbit, humiliating the United States on a global stage. This satellite was supposed to prove America could recover. And now its most important instrument was behaving like broken junk. Mounted on board Explorer 1 sat a Geiger counter designed by physicist James Van Allen. Its job was simple: measure radiation levels in near-Earth space. The expectation was straightforward. As the satellite climbed higher into orbit, radiation levels should rise gradually. The detector would record that increase and send clean telemetry data back to Earth. At first, everything looked normal. The paper strips spilling from mission control showed healthy spikes, exactly where the instrument should be working. Then came the anomaly. Without warning, the sharp upward lines suddenly flattened. Perfectly horizontal. Dead silent. The instrument appeared to stop functioning completely. And that was where the real problem began. A failed Geiger counter was not a minor inconvenience. It was the core scientific payload on board the entire mission. If the detector had malfunctioned during launch vibrations, extreme temperature swings, or orbital deployment, then America's most important post-Sputnik space mission had carried dead equipment into orbit. Days of orbital passes only made the situation worse. Each time Explorer 1 crossed certain regions of Earth, the exact same thing happened. Healthy radiation readings. Then, sudden collapse. Zero. Then recovery. The same pattern repeated over and over again. The telemetry printouts became impossible to ignore. Engineers now faced two terrible options. Either the instrument was broken, or something in space itself was behaving in ways their models could not explain. At first, the failure explanation seemed safer. Mechanical damage made sense. Launch stresses were brutal. Components failed all the time. Maybe wiring had loosened. Maybe the vacuum of space was interfering with internal electronics. Maybe temperature cycling was freezing internal circuits. Except one detail refused to cooperate. The detector kept recovering. A damaged instrument does not break repeatedly with perfect consistency. Yet every orbital pass produced the same sequence. Spikes. Flatline. Recovery. Spikes again. The machine was not dying. It was responding to something. That changed everything. Now the problem was no longer the detector itself. The entire understanding of near-Earth space was under threat. At the time, scientists believed radiation around Earth was relatively predictable. Space beyond the atmosphere was dangerous, yes, but nothing suggested enormous invisible concentrations of charged particles surrounding the planet. The detector was expected to measure radiation, not disappear inside it. Then James Van Allen proposed something deeply unsettling. The Geiger counter was not reading zero because radiation had vanished. It was reading zero because radiation had become too intense to measure. The detector had reached saturation. Its counting system had been completely overwhelmed. The machine was not broken. It was effectively choking. Imagine a speedometer pushed so violently past its mechanical limit that it freezes. That was happening in orbit above Earth. Those perfectly flat lines on the telemetry printouts suddenly meant something entirely different. The visual everyone feared most had become the most important evidence of all. The dead horizontal line was not failure. It was overload. And the consequences were far bigger than one satellite. If Explorer 1 was entering regions dense enough to break trusted radiation instruments, then Earth itself was surrounded by enormous invisible structures no one had detected before. Massive zones where charged particles were trapped by the planet's magnetic field. Natural radiation reservoirs circling the entire world, later named the Van Allen radiation belts. And suddenly, the implications multiplied. Future satellites would pass through these regions. Electronics could fail. Sensitive instruments could overload. Astronauts entering orbit would face invisible exposure risks nobody had calculated. The entire future of human spaceflight had just become far more dangerous. All because one trusted measurement system stopped working. And that final image is what makes this story unforgettable. Inside, NASA engineers spent hours staring at endless sheets of telemetry paper, convinced they were looking at catastrophic failure. Sharp radiation spikes rising normally. Then that impossible, dead horizontal line. The image never changed. But its meaning changed completely. At first, it looked like broken equipment. In reality, it was proof that nature had exceeded the limits of human measurement itself. America's first great space discovery did not begin with successful detection. It began when reality pushed harder than the instrument could survive. Sometimes zero means you found too much.